So it is my pleasure to introduce Shimon Whiteson, who is a professor of computer science at the University of Oxford. His expertise is deep reinforcement learning, amongst other areas of machine learning, and who is also the head of research at Waymo, UK. So Shimon started his academic career at the University of Amsterdam, where he spent a couple of years, and then in 2014 won the prestigious ERC Starting Award. At that point, moved to the University of Oxford as an associate professor, where you established your current group. Shimon is well known for many things, but I think particularly interesting to the multi-agent systems community are his contributions, very ingenious, I must say, in the area of credit assignment. So you might well know his seminal algorithms, QMix and COMA, that solve the credit assignment problem in very ingenious ways. And also he was amongst the first to look into how applying machine learning to learn communication amongst multi-agent or between agents and multi-agent systems. So I believe today we'll be hearing a couple of interesting things about centralized training in multi-agent systems. And I hand it over to you, Shimon. It's a pleasure to have you here.
Thank you. Thank you very much for the introduction and for the invitation to speak today. It's really a pleasure to be here, and at the same time, quite a surreal feeling after 2 years of virtual talks to be in an actual lecture hall with an actual live audience. So when Amanda invited me to speak today, I thought, since it's a keynote talk, I should aim at something a bit more ambitious than just presenting the contents of a single paper as you would in a conference talk. But I was quickly confronted with the realization that I actually only have expertise that's relevant to this audience in one quite narrow topic, which is a cooperative reinforcement learning. So what I want to do today is something a bit different, which is to try to give a broad overview of really quite a narrow topic. So interesting though it may be, I'm not going to talk about competitive multi-agent reinforcement learning. I'm not going to talk about general sum multi-agent reinforcement learning. I'm only going to talk about the fully cooperative setting. And even then, quite a niche area within that, which focuses on a particular set of assumptions about the nature of that cooperation, the way the agents train and what they can observe. So I'm going to mention quite a few different papers by a number of different labs, but the papers that I mentioned that come from my lab, this is all joint work with a large number of collaborators, mostly PhD students and postdocs or former PhD students and postdocs in my lab, but also other colleagues at Oxford and elsewhere. So let's jump right in. Here's my obligatory motivational slide. So cooperative multi-agent reinforcement learning is an important topic because many real-world multi-agent systems either are fully cooperative, like a team of robots in a warehouse, or they contain subgroups that can be usefully modeled as fully cooperative, like a fleet of autonomous vehicles sharing the road with human drivers. Now, deciding to focus on the fully cooperative setting actually doesn't narrow things down very much. There's still a huge range of possible assumptions that can be made about what the agents observe, how they are trained, how they are rewarded, and so on. So back in 2015, when my research group decided to focus on multi-agent reinforcement learning, I started advocating for a setting which is now commonly known as centralized training and decentralized execution. And this setting was memorialized in this slide, which was made by Jacob Forster, who at the time was a PhD student of mine. So as I already mentioned, it's multi-agent and it's fully cooperative. It's also partially observable, which means every agent has its own private, partial view of the true state of the world. And as we'll see, this partial observability is actually key for making the problem fundamentally multi-agent. In addition, we're going to require that the policies that the agent learns, that the agents learn, can be executed in a decentralized way. That means when they're executing their policies, they need to condition only on their private observation history, not on anything that was observed by other agents. However, we're going to assume that the training, the learning of these policies occurs either in a simulator or some other safe setting like a laboratory, which means we are able to centralize that training process. So during training, the agents can share observations, they can share gradients, they can share parameters. Basically, there are no rules as long as the result of learning are these decentralized policies that can be executed according to this decentralized constraint. Now, I've become quite an evangelist for this setting because a core belief of mine is that in order to make progress on hard problems, we have to make the right assumptions. And the right assumptions are the ones that give us a lot of leverage on a hard problem, but still mostly or approximately hold in the real world in the problems that we actually care about. And this CTDE setting is an example of such an assumption, because in the real world, we don't train robots tabula rasa. In the real world, we train them in a simulator or a laboratory first. And the centralization that enables gives us potentially powerful leverage on this difficult problem. But when I started advocating for CTDE, it wasn't coming out of nowhere. It was inspired by previous work that I had done on the problem of planning in a decentralized, partially observable Markov decision process, or DECPOM-DP. And my longtime collaborators, Franz Oliuk and Chris Amato, they wrote a really nice book on the subject, which I encourage you to have a look at if you're interested in learning more about the topic. So in DECPOM-DP planning, we're given an explicit model of the world, and then we need to come up with a clever planning algorithm that will compute an optimal set of decentralized policies that we can distribute to the agents and allow them to execute coordinated behavior without explicitly communicating in the deployment phase. It's a very interesting and also extremely challenging problem, as the computational complexity is doubly exponential in the planning horizon. Now, in CTDE, all we're doing is taking this planning in the DECPOM-DP setting and changing the planning on an explicit model for learning on samples generated in a simulator or a laboratory. So there's really not very much new here in the setting. But this simple change allows us to unlock the power of deep learning, and this is what has enabled some quite rapid progress in the past few years. So let's formalize this setting, starting with the basics. I'll assume you know what a Markov decision process is, but let me just point out that in our notation, the action is denoted by U instead of A, as A will later be used to indicate the agent. We have our state transition function. We have a reward function. Our goal is to maximize returns, which are cumulative discounted sums of rewards. And we can reason about both value functions and action value functions, which are conditional expectations of those returns. Now, the simplest way to make the MDP multi-agent is the so-called multi-agent Markov decision process, where we assume we have now a set of agents that are cooperating. They all can see the true global state, but they each have their own individual action space. So the only changes here are that our state transition function now conditions not just on one agent's action, but on a vector. I'm using bold here to indicate vectors, a vector of the action choices of all the agents, and similarly for the reward function. Now, you may have already noticed that there's nothing fundamentally multi-agent about the multi-agent MDP. We can think of it as a single agent MDP with a multi-dimensional factored action space, as if there was a single puppeteer agent that was telling all the other agents what to do. So if we want something that's truly multi-agent, not just superficially multi-agent, we need to introduce partial observability, and this is what the DECPOM-DP does. So on top of the multi-agent MDP, we layer this observation function. This observation function depends not just on the true state, which is now hidden from the agents, but also on the agent index A. So what that means is that each agent has in general its own observation function and therefore its own private and partial view of the true state. Because of this partial observability, the agents will typically want to condition their behavior on their whole observation history, which we indicate with tau. And now we're looking for a set of decentralized policies, one for each agent, where each policy specifies the action for that agent conditioned on every possible private history that that agent might have. So the agents need to be able to act given only what they will have privately observed upon deployment. Now, there's kind of two different motivations for this setting. One is what I call natural decentralization, where the actual problem setting imposes these constraints. There's some communication or sensory limitations that prevent the agents from just like sharing every observation instantaneously, using like unlimited bandwidth, error-free, completely reliable communication. So the real world is forcing us to decentralize. And then we have the artificial decentralization where none of those constraints actually exist in the world. But if every agent shares every observation with all the other agents, they're overwhelmed by this fire hose of information, and it makes learning really difficult. So in order to make learning more tractable, we artificially force the agents to focus on some local field of view. In either case, the key thing is that we have centralized training, that needs to result in policies that can be executed in a decentralized way. So one way to get some intuition about the DEC-POM-DP is to think about what I like to call the predictability exploitation dilemma. So you're no doubt familiar with the exploitation dilemma from single agent reinforcement learning. This is a different but related dilemma. So on the one hand, obviously the goal of the agents is to exploit. To maximize their performance, they need to collect a lot of reward as possible. And in a single agent setting, typically maximizing your reward means conditioning on your observations, right? Observations are typically useful. If you see the tiger on one side and the treasure on the other side, you need to go to the treasure in order to get reward. But things are more nuanced in the DEC-POM-DP because the agents upon deployment cannot explicitly communicate. So what that means is that in order to successfully coordinate, they need to remain predictable to their teammates. They need to stick to the plan which was agreed on in the centralized training or learning phase. And this creates this interesting trade-off because if you want to remain predictable, sometimes that means you need to ignore the private information that you've received, even if that private information is really quite useful, quite related to your ability to get reward. Because the more you condition on that private information, if it's unlikely that your teammates will have received similar private information, the less predictable you become to them and the greater a risk of miscoordination with your teammates. So in the extreme case, the optimal policy can even be completely open loop, where you just ignore all the observations you receive because conditioning on them is too risky in terms of miscoordination. So how do we decide when the benefit of exploiting private observations outweighs the cost in terms of predictability? This is one of the central challenges of the DEC-POM-DP. Okay, so one of the interesting developments to follow in the past few years in this area is an arms race between two different families of learning methods. On the one hand, we have Q-learning-based methods, which try to learn an optimal action value function, and then use that action value function to extract behavior which is greedy with respect to that value function and therefore optimal. Or on the other hand, actor-critic methods where we estimate a value function or an action value function of the current policy, and then use that to estimate a gradient of the expected return with respect to the parameters of an explicit policy. Now, again, there's nothing new here. The sort of dichotomy between these two families of methods is familiar from single agent reinforcement learning, but it has some particular implications and trade-offs that are specific to this partially observable multi-agent setting. So what I want to do for the rest of this talk is, first of all, give you an overview of some of the key developments in the Q-learning family of methods, and then do the same for the actor-critic methods, and finally tell you a little bit about the empirical arms race that has unfolded between these methods. So let's start with the first part about the Q-learning-based methods. So the simplest approach that we can take is an approach called independent Q-learning, which was proposed way back in 1993. And the idea is basically every agent is going to pretend that it was in a single agent MDP, ignore the other agents, and just apply Q-learning off of the shelf. So every agent is going to learn its own Q function. There's no attempt in that Q function to actually model the value of joint behavior, to model the other agents or their policies or the value of the resulting joint actions. Just every agent reasoning about the value of its own actions. And what this means is the agents are treating the other agents as if they were part of the environment. Now, because we have centralized training, we can immediately improve upon this algorithm by using parameter sharing. So even though each agent is learning independently, actually, when they perform an update, they're performing an update to the same set of shared parameters theta. So these parameters still parameterize a individual Q function that just reasons about individual actions, but it does so using the gradients from all of the agents. Now, this shared policy can, the agents can still behave differently because they will receive different inputs. They'll have different private observation histories. And those histories can also include the agent index, which allows the agents to behave arbitrarily heterogeneously despite completely sharing parameters. Now, it's reasonable to ask, if the agents are sharing all the parameters, in what sense is independent Q-learning really independent? But it is still independent in the important sense that these value functions only reason about the behavior of an individual agent. So there's no attempt to model the joint value function. Obviously, this is a naive approach. A well-known limitation of this approach is that because the agents are treating the other agents as part of the environment, This results in essentially a non-stationary MDP as the other agents change their policies and all your convergence guarantees go out the window. Nonetheless, it's quite a strong baseline that can be surprisingly difficult to beat in practice. Okay, so if we want to do better than independent Q learning, a natural idea is to centralize this Q function. Rather than just estimating the value function for an individual agent, let's estimate the value of the joint behavior of the joint policy. So this value function, this joint value function or total value function called Q tot, conditions now on the joint observation history of all the agents and estimates the value of a joint action. So what's appealing about this is it gets around this non-stationarity issue. We're now taking a global view of the system. So this problem of non-stationarity that comes from an agent's egocentric view totally goes away. However, we trade that for a different problem, which is that even if we could learn the optimal joint action value function, it's not clear what we would do with it. Because remember, we need to be able to execute in a decentralized way. So how do we take this optimal joint action value function and use it to extract optimal decentralized behavior? That's the challenge that we now face. And it turns out in order to do this, we're going to need to be careful about how we construct this joint value function so that it's amenable to a decentralized argmax. Okay, now the way that we go about doing that is closely tied up with another issue, which is called factored value functions. Now, factored value functions have a long history in single and multi-agent, not only reinforcement learning, but decision theoretic planning. And the idea is that we estimate this, in this case, joint value function by assuming that it decomposes as a sum of simpler local value functions where each local value function depends on only a subset of the agents and the team. So this is captured in a coordination graph, where coordination graph is simply a factor graph where the factors are these local value functions and the variables are the action choices of the individual agents. So just like a probabilistic graphical model, a coordination graph captures conditional independence properties. So here, for example, agent 1, if it knows the action choice of agent 2, it can select its own action without caring about the action choice of agent 3, due to the conditional independence expressed in this coordination graph. So these factored value functions are very powerful because they reduce the number of parameters that need to be learned, thereby speeding up learning and improving generalization. In addition, they also make it easier to compute the maximizing joint action. Given a value function, what is the joint action which maximizes that value function? To compute that, we can use our favorite message passing algorithms for map inference on probabilistic graphical models and apply them to these coordination graphs. Okay, now, as is often the case, the DeepMind was the first to deep learnify this idea using an approach that they called value decomposition networks. So in value decomposition networks, they adopt the most extreme possible factorization, a factorization in which each factor contains only one agent, leading to the following, to the disconnected factor graph, coordination graph shown in this figure. Right, so this is obviously, and I guess the other thing worth mentioning is that now each of these local value functions is represented by a deep neural network. Now, obviously, this is an extremely restrictive factorization, but it has, as a side effect, one very important property, which is that it enables this key property I said we were going to need for these joint value functions, which is the decentralizability of the max and argmax. So the idea here is that if we adopt this extreme factorization from VDN, then when we need to perform a maximization over this joint value function, rather than having to iterate over this combinatorially large joint action space, we can instead just separately perform a much easier maximization over each agent's action space separately, and then just sum up the result of the results of those maximizations. And because of the VDN factorization, this summation will yield exactly the same result as if we had done the more expensive exhaustive maximization. Similarly, if we need to perform an argmax, we can do that by performing an argmax separately for each agent and then compiling the results into a vector, and that vector will correspond to exactly the same joint action we would have gotten if we'd done the exhaustive joint argmax. So, if we perform DQN now with this centralized Q function, then when we need to bootstrap and perform this maximization, we can do this in a computationally efficient way because the maximization decentralizes. In addition, when we've learned this value function and we need to deploy and actually execute it in a decentralized way, we can do that as well because this argmax decomposes into a set of simpler argmaxes, each of which can be performed by each agent separately using only its local value function. Okay, so we developed a method called QMix, which was a follow-up to this work. And the idea behind QMix was to try to relax the restrictive factorization of VDN while preserving this handy property of being able to decentralize the max and argmax. And it's based on a very simple observation, which is that if we want to be able to decentralize the max and argmax, we don't need to have a factorization as strict as VDN. All we need to do is enforce this monotonicity constraint, which says that the partial derivative of our joint value function with respect to the local value function of any individual agent needs to be non-negative. And this needs to hold for all agents. Now, a potential source of confusion here is we're talking about discrete action spaces. So these local value functions are actually only defined at a discrete set of points. So what does it even mean to take a derivative with respect to it? Well, this figure shows what's happening. When we take these local value functions and combine them together, we combine them with what we call a mixing function. Now in VDN, that mixing function is just a summation, but the point is the mixing function can be anything as long as it obeys this monotonicity constraint. So here in this figure, this color gradient illustrates a monotonic mixing function. So this is a mixing function that obeys the monotonicity constraint because it increases monotonically with respect to that local value function of either agent. And we can think of this mixing function as being defined with respect to continuous valued local value functions. But in practice, the inputs that are supplied to it will only ever occur at a discrete set of points corresponding to the values of the discrete set of actions available to each agent, which each agent can now easily maximize over thanks to this decentralizability property that we've ensured with this monotonicity constraint. Now, when the students in my lab first proposed this idea to me, I was pretty skeptical. In fact, I was convinced that it would never work. And my argument was, if we restrict ourselves to monotonic mixing functions, we're going to have the same problem that we already had with VDN, which is that the value function won't be able to capture the benefit of coordination. By definition, if each agent can select its action without considering the action choices of the other agents, then there cannot be any synergistic benefit to coordinating with those other agents. So that's illustrated with these normal form games shown here. So on the left, we have a linear and monotonic value function, which can be represented with both VDN and QMix. In the middle, we have one which is nonlinear, but still monotonic. So this can be represented by QMix, but not VDN. And on the right, we have one that is both nonlinear and non-monotonic, so neither VDN nor QMix can represent it. And my point was only this game on the right actually involves coordination between the agents, because only in this game on the right does the action choice of one agent actually depend on the action choice of the other agent. So the question then becomes, should we care about these games in the middle? Because these games in the middle are the only ones that QMix can represent better than VDN. And my argument was, well, not really, because even if VDN can't represent the value function to this game exactly, it could approximate it with the value function of the game on the left. And then when you perform an argmax with respect to that approximate value function, you'll get the same result as if you had used QMix. So what's the point, basically? So I thought this was a clever argument, but the students had an insight which I had overlooked, which is that the value function that you learn is not just used for action selection. It's also used for bootstrapping. So if we take a look at the DQN loss function shown here, it's a mean squared error between the joint value function and a target. And the target is computed by bootstrapping off of the value of the next state. So the value function that you estimate is used to supply this crucial term in the target. So the point is, even if QMix can't represent a value function that's enough better than VDN to improve action selection at the current state, it can estimate the value function better in a way that leads to less bootstrapping error, and therefore better value estimates for the states that appear earlier in the sequence, and therefore better action selection for those earlier states. So the benefits of improved value estimate propagate forward to the earlier states, leading to real performance improvements. So let's look a bit more closely at how QMix works. So in the middle, we have a figure which shows how everything works. There are three networks: an agent network, a mixing network, and a hypernetwork. So the agent networks, they're used to estimate the local value functions for each agent, just like in VDN. So this is just a generic deep neural network with feed-forward and recurrent layers. And again, they share parameters just like in independent Q-learning and in VDN. Then instead of summing them as we would in VDN, we send them to this mixing network, the output of which is this joint value function QTOT. Now this mixing network, which is shown here on the left, it represents QTOT, and it does so using non-negative weights. By using non-negative weights, we enforce the monotonicity constraint required for decentralizability. But the weights of the mixing network are not specified directly. Instead, they're specified indirectly using a hypernetwork shown in red. And the reason for that is so that we can more flexibly condition on the global state S. So during the execution phase, we can throw away the mixing network. All we need are these agent networks for the agents to perform decentralized argmaxes. So the mixing network can condition on the global state, since we only need that during the centralized training phase. And by feeding the state into the hypernetwork rather than directly into the agent network, we can more flexibly condition on the state, getting around this monotonicity constraint. So in principle, we can have a different mixing function for every state in the world. So there have been a lot of follow-up methods to QMix, which I don't have time to go into. Let me just try to briefly sort of give you a taxonomy of them. There are kind of three categories. One is, the first one is better representations. So just like QMix has a better representation than VDN, there are follow-up methods that try to get a more expansive representation than QMix, such as Qplix and Maven. There are also methods that try to improve exploration. So given the representational constraints of QMix, can we still try to converge to a better optimal value function by doing more extensive or more intelligent exploration? That's what methods like Maven and Uneven do. And then finally, there's a family of methods that try to leverage unrestricted value functions. So basically the idea is at the same time that you learn a QMix style value function, you also learn an unrestricted joint value function, which is not decentralizable, but can be used as a guide to, for example, derive loss functions that can improve the learning of your QMix style value function that is decentralizable. Okay, let's move on to then part two, which is about the actor-critic family of methods. So again, let's start with the simplest possible approach, which is an independent approach. So independent actor-critic is a method which is analogous to independent Q-learning. We just replace Q-learning with a single agent actor-critic method. So the actors are executing decentralized policies, which can again share parameters, but now each actor has its own critic. And this critic, like in independent Q-learning, it only estimates the value function of a single agent. So this is just the action of a single agent and one agent's observation history. There's no attempt to model joint values. But we can do parameter sharing in both the actor and the critic now. So again, this is the simplest approach. As on the Q-learning side, if we want to get more clever, a natural thing to do is to centralize the critic. So we have a centralized critic that conditions now on the joint state and the joint action observation history, and estimates the if it's a action value critic, it estimates also the value of a joint action. So centralizing the critic is a natural idea because the critic is only used during training. So once we've learned the policies, we can throw the critic in the bin, and basically anything you discard before the execution phase is a great candidate for centralization. So one way I like to think about this is that actor-critic methods are appealing anytime you face what I call a hard greedification problem. So for example, if you have a continuous action space, even if you had the optimal value function, just finding the action which maximizes that continuous value function would itself be a hard optimization problem. And in fact, continuous actions are the sort of canonical use case for actor-critic methods. Well, here we have a different hard greedification problem because we're learning this centralized joint value function. And from that, we need to extract these decentralized policies. So actor-critic methods can help us do that by using this value function to estimate a gradient, which can then be used to update our decentralized policies. So we developed a method of this flavor called COMA, counterfactual multi-agent policy gradients. It uses this idea of a centralized critic and decentralized actors and also has something we call a counterfactual baseline, which addresses the multi-agent credit assignment problem. So basically, if there are a lot of agents, or if the agent's behavior is sufficiently stochastic, it can be hard for any agent to tease apart what its contribution was to the reward that was received by the whole team. So in COMA, we basically view this as a variance reduction problem. And we introduce this counterfactual baseline. It's a covariate, which has expected value of 0. So it doesn't introduce any bias into the gradient estimate, but because it varies together with the value function, it reduces the variance in the gradient estimate. And it does that by helping the agent tease apart its contribution to the reward by considering a bunch of counterfactual scenarios, averaging across these counterfactual scenarios in which the agent in question had taken a different action than the one it actually took, while its teammates' actions were held fixed. So there's another method in this same family called multi-agent deep deterministic policy gradients, or MADDPG. So most actor-critic methods, they assume stochastic actors, stochastic policies, and they use what's called the score function estimator to estimate the gradient. So here, for example, you have this gradient of the log policy probability. This is a score function that appears in the policy gradient theorem. But in a deep deterministic policy gradients, we instead assume a deterministic policy and directly use a Jacobian, the Jacobian of this deterministic continuous valued action with respect to the policy parameters to compute the gradient. And so MADDPG is a multi-agent extension of that, where we basically apply this deterministic policy gradient for each agent separately, but with respect now to a centralized value function. So this is kind of analogous to COMA, but for the case of deterministic continuous valued policies. Now, both of these methods are predicated on the assumption that centralized critics are preferable to decentralized critics. They're preferable to an independent actor-critic approach. And this is a natural assumption to make because the centralized value function, it can capture the value of coordination between the agents. So it would seem to have to be more informative and more useful. However, there was a fascinating recent paper this year which basically proved that this assumption was wrong. So what they show is that if we assume that the critics are correct and that the policies are parameterized in the same way, then the expected value of the gradient that we'll receive when we use a centralized critic and when we use a decentralized critic are exactly the same. So in expectation, these critics perform the same. So essentially, the decentralized critic is marginalizing across the action choices of the other agents, which doesn't affect anything in expectation, but can lead to different bias variance trade-offs. And this is where the difference between these two types of critics really emerges. The analysis is not exhaustive. It, for example, doesn't consider the case where critics are based on state value functions V instead of Q, which often perform best in practice. But nonetheless, it's a very interesting sort of wake-up call to those of us who have been assuming that centralized critics are necessarily better. So one way to get intuition about this is to think about the climb game, which is a sort of classic matrix game that was originally proposed by Klaus and Boutelier and is analyzed by Liu and all in their paper. So this game illustrates what's sometimes called relative overgeneralization, but you can really just think of it as like the problem of local optima in a multi-agent setting. So imagine you have two agents and their current policy is that they both select action U2. So they're getting a payoff of 7, but they'd like to get this better payoff of 11. Well, if any agent unilaterally tries to change its action to A1, unless its teammate happens to explore in the right way at the same time, it's going to be punished for doing so. So the gradient is going to actually point it away from where it needs to go in order to get the best payoff. So what they show in the Liu et al. Paper is that if you use a centralized critic, you can learn the values in this payoff matrix perfectly, and that happens quite quickly. But having this perfect critic doesn't help you at all because the gradient that you're following is updating a set of decentralized policies and will still get you stuck in this local optimum. So the problem is the decentralized policy, and centralizing the critic isn't going to fix it. However, that's not the end of the story either. So we recently published a paper called FACMAC, Factored Multi-Agent Centralized Policy Gradients. And the idea is basically like, look, we can't centralize the policies. We can't centralize the actors because the whole point is to learn decentralized policies. But in addition to centralizing the critic, we can also centralize the gradient. And the key here is to start from MADDPG. We can't start from a method that uses a score function estimator, otherwise centralizing the gradient is going to give us a gradient that it's a sum of exactly the gradients we would have gotten with a decentralized approach. It makes no difference. But with MADDPG, remember the gradient is based on this Jacobian. And now we can just centralize that Jacobian. So we can just use the Jacobian now of the joint action with respect to our policy parameters. So our policy gradient now becomes a product of this Jacobian of the joint action with respect to our centralized value function, a gradient of the centralized value function with respect to that joint action. So this critic is not only centralized, but it's also factored. Now, in the actor-critic setting, we don't need to factor the critic in order to achieve decentralizability because the critic is only used to compute a gradient. It's not used in execution. It doesn't need to be factored. But factoring it can still improve the quality and generalization ability of the critic. But we can now factor it however we want. We don't have to obey a monotonicity constraint because we're not using it for decentralizability. So these two ideas, centralizing not just the critic, but the gradient, and using a factored unconstrained critic, this is kind of the latest step in the actor-critic setting. So the final piece of the puzzle, which I can't avoid mentioning, is the rise of methods based on proximal policy optimization for multi-agent RL. So really quick bit of background, trust region policy optimization, or TRPO, is a family of policy gradient methods that instead of maximizing the expected return, they maximize this surrogate objective. And this surrogate objective has this key term in it called lambda, which is the ratio of the policy probabilities before and after the policy update. And then they also constrain the updates to this trust region, which is enforced by the total variation distance between the policy probabilities before and after the update. Now, proximal policy optimization, or PPO, is a sort of more practical alternative to TRPO, where we dispense with this expensive constraint and just maximize a clipped version of this surrogate objective. And PPO has been an extremely empirically successful algorithm in single agent reinforcement learning. It's only a matter of time before it made the crossover to multi-agent RL. So we proposed a paper, we wrote a paper last year that proposed an independent version of PPO that showed a surprisingly strong performance for an independent learning algorithm just by using PPO for each agent. And then this year, you et al., they proposed MAPO, which is a multi-agent PPO method that uses a centralized critic. So, here we have the objective. It's the same as the PPO objective, but we just have a separate one for each agent. And, this advantage function is computed either with a decentralized or centralized critic, depending on whether we're talking about IPPO or MAPO. Now, there's one problem with these approaches, which is that, they all use what we call independent ratios. So this ratio between the policy probabilities is computed separately for each agent. And this induces non-stationarity because every agent is not taking into account the fact that the other agents are also updating their policies, leading to other ratios as well. This violates the assumptions underlying the monotonic improvement guarantee that motivates the use of this surrogate objective. In fact, a direct application of the analysis that yields to this monotonic improvement guarantee would imply the use of joint ratios. So the ratio would be computed on the joint policy, which is not what IPPO or MAPO does. However, hot off the presses, we have a new paper which shows that the fact that these methods enforce trust regions actually constrains the non-stationarity that's introduced as a result of these independent ratios. So that enables us to derive a new monotonic improvement guarantee that applies to IPPO and MAPO. So basically, despite their use of independent ratios, they implicitly adhere to a centralized trust region, and that enables us to ensure monotonic improvement. So the size of this joint trust region depends on the number of agents and the value of some clipping hyperparameters. And our empirical results show that the optimal value of those clipping hyperparameters is highly sensitive to the number of agents, which is exactly what this theory would predict. Okay, so let's turn to the third and final part of the talk, which is a bit about the empirical arms race that has occurred between these methods. So most of this arms race has focused on the StarCraft multi-agent challenge, or SMAC, which is a benchmark problem for DEC-POM-DPs that we introduced a few years ago. So SMAC is based on StarCraft 2, which is a real-time strategy game. You've probably heard about AlphaStar, which is DeepMind's wildly successful StarCraft playing agent, is also based on StarCraft 2. But the problem setting is actually only superficially similar. So AlphaStar is like a puppeteer agent, a single agent that controls all of the units, like in a multi-agent MDP. Whereas in SMAC, we're focused on DEC POMDPs. Each unit is controlled by a separate agent. So as we've seen in single agent settings, having good benchmarks is really key to driving progress. So that's why we created an open source SMAC to try to sort of spur progress in the field. And a lot of the empirical results I'm going to talk about are in that setting. So as we know, to make a setting truly multi-agent, it has to have partial observability. So in SMAC, we enforce this by introducing a site range, so the agents have a limited field of view. There are 14 different maps in the SMAC benchmark problem. We have maps where the agents have the same units as the enemy. The enemy is controlled by a fixed game AI. It's a fully cooperative setting with a fixed opponent. And we have maps where the other agents are, where the opponents are of the same type, but there are more of them. And then we have asymmetric maps where the opponents have different types of agents. So I don't want to bore you with dozens of plots, so I'll just show you an overview plot from the journal version of our QMix paper. So on the y-axis here, we have the number of maps out of 14 that each method has the best policy for at different points during training. And as we can see, QMix is really performing well. It learns faster and also tends to learn better policies in the long run than the other methods. Keep in mind, to have the best policy, you have to be epsilon better than the other methods. So even when on the maps where QMix isn't winning, it isn't losing, it's just basically tying. That's why the number of maps doesn't add up to 14. But the take-home result here is QMix is a very strong method empirically. We did a whole bunch of ablation experiments, which I won't go into, but I'll just mention one ablation, which is where we compare QMix to QMix lin. It's just QMix where we replace the mixing function with a single linear layer. And as you can see in most maps, QMix does better than QMix lin, which is what you would expect. However, here's where things get weird. If we actually look at the mixing functions that we learned, they look really close to being linear. So we've done this analysis on a number of maps. I'm showing you on this map in particular, because on this map, there are only 2 agents, so it's easier to visualize the value function. So this is the mixing function at the first time step and at the 50th time step. And it looks really close to being linear. So what's going on here? We did some extra analysis to try to get to the bottom of it. And what we did was we compared QMix not only to QMix lin, but to another method called QMix2 lin. It's kind of in between the two. Like QMix lin, it uses only linear layers, but like QMix, it has 2 layers. Now, you know, your machine learning textbook will tell you that putting linear layers on top of linear layers doesn't improve the representational capacity, because the linear combination of linear functions is still just a linear function. However, what your machine learning textbook won't tell you, but any machine learning practitioner probably knows, is that adding those layers will change the learning dynamics, and that those changes can actually be quite favorable. And that's what's shown in this plot. This isn't actually a reinforcement learning experiment. This is just a supervised learning experiment of trying to predict the values of a fixed value function. So the y-axis is just a mean squared error. And what we can see is that QMix2 lin learns much faster than QMix lin. So the benefit here is coming from the extra layers, not the nonlinearity. Now we can, and this result holds up when we look at RL. So if we do QMix2 lin, we get performance just as good as QMix and better than QMix lin. Now we can try to force QMix to learn more nonlinear mixing functions by changing the activation function from LU to TANH. And if we do that, we do indeed see more nonlinear mixing functions. But that does not translate to better performance. So as you can see here, these change in activation function does not result in better performance on these SMAC maps. So the take-home message here, QMix decisively outperforms VDN and IQL, independent Q learning, but not for the reasons that we expected. It seems that richly parameterizing the mixing function is really important, but much as we might wish it was otherwise, nonlinearity in the mixing function doesn't seem to be important, at least in SMAC. We also see that QMix decisively outperforms COMA, but there's an important caveat here, which is that there's a confounder in these experiments. QMix is an off-policy method. It's a Q learning method, so it's off-policy, whereas COMA is an on-policy actor-critic method. So is the difference between using actor-critic versus Q learning, or is it the difference between using on-policy and off-policy? So to try to get at this issue, we did some more controlled experiments, some controlled comparisons by starting from MADDPG. So MADDPG, because it learns a deterministic policy, it has to use a stochastic policy for exploration, which means it has to be off policy. So this is an off policy actor-critic method, but it uses continuous action. So to compare it to an off policy Q-learning method, we have to make a continuous action version of QMix. So we created this method called COMIX. It's a continuous action version of QMix. It uses a cross-entropy method to approximately maximize over the continuous action space of each individual action when performing the decentralized argmax. Now, because we have continuous actions, we can't evaluate it in SMAC because that is discrete actions. So we created a different benchmark we call multi-agent Mujoko. These are simulated robot control tasks, but decentralized. Basically, every joint is controlled by a different agent that has only local observations. This is a DECPOM-DP in simulated continuous action robot control. And what our experiments show is that COMIX indeed performs much better than multi-agent DDPG. So that's another point for Q-learning methods. However, if we try FACMAC, which remember was basically multi-agent DDPG with this centralized gradient and a factored critic, we see that it performs even better than COMIX. So it seems that if anything, the key issue here is having a good factorization of the value function rather than whether you use Q-learning or an actor-critic method. But that's not the end of the story either. If we go back to SMAC, we still have the problem that if we divide the maps into easy maps, hard maps, and super hard maps, the performance of the methods I've discussed on the super hard maps is really embarrassingly poor. So most of the methods just completely flatline. They don't learn anything. QMix is the only one that makes any progress, and it does that on only 2 of the 5 maps. And even then, the performance is not very good. So that suggests that SMAC is far from being solved. However, this is where PPO really enters the picture. So this figure is taken from the Yu et al. Paper where they proposed a MAPO, and it shows that both IPPO and MAPO can perform really well across all 14 SMAC maps, including the super hard maps. If you look at MAPO in particular, the performance, the win rates here are astonishing across all 14 maps, just by using PPO as a starting point for the method. So this is a real win for the actor-critic family of methods. However, that's still not the end of the story. If you thought the story here was QMix pulling ahead for an early lead only to be overtaken by actor-critic methods based on PPO, you would be wrong, because there was a fascinating paper this year by Hu et al. Where they showed how important the implementation details are. And they showed that if you implement Q-learning with all the right bells and whistles and you tune the hyperparameters properly, it also can get astonishing win rates on SMAC, even including all of the super hard maps. So it outperforms a whole family of methods, most of which were specifically designed to overcome deficiencies in QMix. So I continue to be caught off guard by the surprising resilience of QMix as a method. So to wind up, let me just say a little bit about next steps. I think at this point we can say that SMAC is solved, and there's no longer a lot of value in continuing to publish papers based on SMAC. The field is ready for a new challenging benchmark problem, and there are a number of candidates available for that. I mentioned already multi-agent Mujoko poses some new challenges. There's something called Google Football, which is an extremely challenging DECPOM-DP hierarchical multi-agent control problem. Another way to think about it is just to come up with a SMAC 2.0. And it may be that we don't have to change SMAC very much in order to create fundamental new challenges. So we published a paper this year which showed that even small changes to the reward function in SMAC, so for example, penalizing the agents when one of their teammates dies, as opposed to only penalizing, as opposed to only rewarding them when one of their opponents dies, is enough to really exacerbate this problem of relative overgeneralization and to really trip up even state-of-the-art methods. We're also thinking about SMAC with more stochasticity and partial observability, as this sharpens the contrast between the private knowledge of one agent and the common knowledge of the team, thereby heightening this predictability exploitation dilemma. Yet another option is not to change the software at all, but just to change the metric by evaluating performance only after a very tight budget of, say, 100,000 samples, which would be enough to totally decimate existing methods which need millions of samples. And finally, we can also think about multitask or meta-learning versions of these problems that go beyond training a separate policy from scratch for each map. So I'll leave it at that. If you're interested in some of the work that I described, I encourage you to take a look at some of our papers on the subject, which are listed here. Thank you very much for listening. I'd be happy to answer any questions.
All right, thank you very much, Shimon. We're ready for a couple of questions from the audience. Yep, Alex.
Thanks so much for your talk. I have been starting to study this problem as well. And do you agree, or what's your opinion on the credit assignment problem being seen as a causality problem especially in environments where you have global reward, you're trying to find out, which actions cause that possible future reward to happen. And do you see like long time horizons as being an obstacle for these algorithms to perform?
Yeah, good question. I do think it makes sense to think of it as a causality problem. So when the agents get tripped up about credit assignment, it can be viewed as them learning spurious correlations. Like I said, I also like to think about it as a bias variance problem. So basically the credit assignment is hard because of variance in the gradient estimate. So that's what I liked about the COMA method, is it kind of unifies this variance reduction covariate literature from the policy gradient community with this like difference reward credit assignment literature from the multi-agent community. However, I have to say, COMA has not really held up empirically. We haven't been able to get good empirical results with it since we published the paper. I mean, the results are not terrible. They're consistent with what we published in the paper, but in all of these head-to-head competitions, it's always blown away by QMix, or even there's a simpler actor-critic method called Central V, which just uses a centralized critic that estimates V, and no clever baselines and no action value function at all. It's an extremely difficult baseline to beat. And I don't know why that is. I have to conclude that at least on SMAC, multi-agent credit assignment is apparently not very hard. So it's possible that out there's some other challenging benchmark problem where multi-agent credit assignment is really hard and COMA would shine. But despite some actually quite deliberate sort of problem engineering, I haven't been able to find it. So I don't know what to conclude from that. Maybe it's just needed in very different problem settings.
Thank you.
Great. More questions from the audience? Yeah, Andy.
Oh yeah, thank you. So your results are very kind of empirical on these game settings in particular, but I have very little feel for what's actually been learned by these agents. Whether there's anything sort of that might be transferable to real problems and so on. And do you have any videos or anything that give us any idea at all of just what, for instance, what can a decentralized at runtime agent not do that a centralized one can, for instance, and what surprising things can it still do?
Yeah, that's a good question. I apologize for not having brought any videos. So I can make a couple of qualitative observations. So one is, it really does seem like the agents learn coordinated behavior. So there are two strategies which they clearly learn. One is called focused fire, which is basically where the agents coordinate on which opponents they're going to fire on. And there are synergistic benefits to if more than one agent fires at the same time. There's also a strategy called kiting, where basically one agent draws fire from the opponent, allowing the other agent to position itself in a way as to attack that opponent. On the other hand, the success of these independent methods suggests that maybe SMAC is not as hard as we thought it was. Like maybe it's a problem which superficially looks like one that really requires coordination among the agents, but maybe it's really like too easy of a problem. That's something that I've worried about quite a bit. But we do see that these more complicated strategies are learned, and we see methods like QMix consistently outperform more naive methods like independent Q learning. So there is something there. Another thing that we've done is we've done some experiments that vary the size of the site range. So one hypothesis that we were worried about was that like the partial observability was basically negligible. In principle, it's partially observable, but if the site range is too big, then in practice, the agents already observe everything they need to. But what we see is that performance really does change as a function of that site range. and that performance, like basically the results validate this idea of artificial decentralization that I mentioned. So if you expand the field of view to be too large, the performance drops off because the agents are overwhelmed by having too many observations. Yeah, if the sight range gets too small, then obviously the performance drops off as well. So it's not the case that the problem is so simple that it can be solved with like totally open loop policies, because if the sight range is too small, it really hurts performance. So that's the best I can do.
Several questions. Yeah, Jan.
Thank you. So I have a question about the benchmarks that you proposed. So you mentioned there's this robot football simulator. I was wondering, what is your opinion on using that as a benchmark in general, multi-agent research, specifically because there are competitions such as RoboCup? Do you think something like that would be yeah, a good benchmark?
Yeah, so I think the RoboCup community has probably developed a lot of techniques that would be extremely useful, and that there should be better interaction and synergy between that community and the deep multi-agent RL community. I think I view Google, I hope that Google Football is not like ignoring that community and reinventing the wheel. I hope what it's doing is basically providing software infrastructure that makes it easier to do the kind of thing the RoboCup community has been doing, but like in a way that joins up with deep reinforcement learning libraries that already exist. I think, so having played with it a little bit, my impression is the fundamental challenge there is hierarchy. Basically, you can't get anywhere in Google Football without hierarchical policies. Like you can't just reward the agents for scoring goals and then have them learn from scratch. You have to decompose it into subtasks. They have to learn how to kick on goal. They have to learn how to pass to teammates. And then when they have those skills, they need to learn how to assemble them into agents that can actually play football. So in a way, that's a good thing, because hierarchy is a fundamental challenge, and it's something that's clearly missing in SMAC. So that's a viable candidate for sort of like the next big challenge. The thing that makes me a little bit pessimistic is I don't think that hierarchy is anywhere near solved in single agent RL. And that's one of these topics where there's been decades of people coming up with clever algorithms and cool ideas and nothing that really, really works empirically. So there's a risk that it's too soon, that we need to go back to basics and figure out hierarchy in single agent RL before we can tackle something like Google Football.
There's another question from Sabine.
Thank you very much for this rundown of the state of the art. That was very useful. Can you comment on the limitations there might be and how many agents you can treat using this method? And as well, if there's any benchmarks that relate to that first slide of where we want this to go in the longer term, whether it's warehousing or driving or other applications?
Yeah, so because we have parameter sharing, in principle, scalability in the number of agents should not be too challenging. I think a lot depends on how heterogeneous those agents are. So I mentioned with independent Q-learning, when we first introduced parameter sharing, in principle, the agents can behave totally heterogeneously because they can condition on their agent index. But of course, the agent index is like a very poor feature. So I think if you have a lot of agents and the agents are really heterogeneous, then to scale, I think what you need is to have richer features. So rather than supplying every agent with an agent index, you need some rich feature vector that describes the agent's type. And that would allow you to then generalize across like a huge set of agents of different types. I would imagine, I'm only speculating here, but I would imagine that when you have many agents, multi-agent credit assignment then really does become an issue. And I don't know if that would be like the opportunity I've been waiting for a method like Coma to shine, or if that would be the setting which shows that a method like Coma is nowhere near good enough at credit assignment to solve it when it's a real problem. That we'll have to see.
I'm going to interject with a quick question before taking more. So I'm really interested in the problem of sim to real. So obviously you're using centralized training here because it's extremely effective and we're assuming we have global observations. But I presume what will happen at some point is we're going to take these policies, we're going to deploy them, we're doing decentralized execution, and we're going to continue fine-tuning the policies, right? But at that point, we don't have the global observations anymore, no global rewards, essentially, right? So how do we take those policies and keep on learning as we're deploying the systems and actually perhaps receiving local rewards, and perhaps not, well, we don't have homogeneous systems anymore at that point. We might be actually running decentralized heterogeneous systems. So how does this connect to the actual deployment problem? Yeah, that's a great question. So, I mean, people sometimes criticize this setting, because the training happens in this centralized way. Whereas from my perspective, it's not an either or, it's like the best of both worlds. Like what you would do in the real world is centralized training and then also decentralized fine tuning. In principle, you can use any algorithm to do it, but like, I guess an important question I haven't thought very much about is how could you design your centralized training algorithm so that it will interact synergistically with the decentralized fine tuning you're going to do later? And I don't know the answer to that. The thing that comes to mind off the top of my head is that like, if you use a method like IQL, the value functions that you learn might not be very good because of non-stationarity and because they're only local value functions, but they are actually value functions. Whereas with VDN and QMix, calling those local value functions is actually a bit of a misnomer, because the loss function is only applied to the joint value function after mixing. So really, they're just like intermediate scores or utilities, and they're not calibrated. They could be anything. And that could be an argument against using such methods if you're going to fine tune, because you wouldn't be starting from calibrated value functions that would be a good starting point for fine tuning later. Yeah, it's a great insight. Thanks. Yeah, I think Roderick, you had a question.
Thanks. Yeah, so my question relates a bit to the QMix monotonicity constraint. So if the constraint is not fulfilled, I guess you could still construct a different value function that potentially helps, like for a soccer game where you have maybe intermediate goals and maybe you sacrifice something, an agent takes something that only in the long term pays off and so on. So I would like to, can you give us an intuition on problems where you can't decentralize whatever, almost whatever value function you use, as long as kind of the final objective, the number of goals kind of stays the same, of course.
So like the factor graph that I showed when I talked about factor value functions is an example there. So basically, agent one's action choice depends on agent two's action choice because they both participate in the same factor. And therefore it depends indirectly on the action choice of agent three, because that will influence agent two's action choice and so on. So in addition, when I showed the three matrix games to explain my skepticism about the student's idea of QMix, the one on the right, then you have these two local optima. What action you want to take depends on the choice of the other agent. So there's no way to perfectly represent that value function using any value function that obeys this monotonicity constraint.
Mm-hmm. One last question before we wrap the coffee. Yep.
So thank you for the great talk, very interesting. Excuse me if the question might be naive. I'm not in the field of that method, or I don't know the benchmark problem actually. So how is it if we would just alter the benchmark a bit? So if I understood you correctly, a map means it's exactly the same situation with the units being placed at the same thing initially. Is that how it is? Because if it is so, how can you be sure that you actually learn a behavior? If I would define a behavior as being deducing an action from what you perceive, and maybe not something like an open loop policy where it just looks like they have this cooperative behavior where they target a single enemy, but in fact they might just rehearse something, knowing what to do at which time instead of what to do in which situation. So could something like this happen, and could we be misled in thinking that it looks different than it is? And maybe to put it more precisely, if you would change the situation slightly, does performance decay drastically, or do we really need to use a completely different map to deteriorate performance?
So there is a small amount of stochasticity in SMAC at the moment, but there isn't enough. And that's a motivation for, as I mentioned, I think in SMAC 2.0, we need to introduce more partial observability and more stochasticity. However, we do already know that it's not the case that open loop policies do well, because we've done these experiments with a changing field of view. And when the field of view is too small, the performance definitely does drop off. I think the lack of stochasticity in the initialization, the initial position of the agents, has a greater effect, not in terms of how closed loop the policy needs to be, but in terms of how difficult the exploration problem is. So we have done some experiments where we change the initial positions of the opponents, and it does cause the methods to fail, but it causes them to fail because of a lack of exploration. And doing smart exploration in this setting is something I've thought a lot about, and we've tried to develop, we've put a lot of energy into developing smart methods for it with quite limited success. So that, I think that's also like quite an open problem.
Awesome. Thank you very much, Shimon. Another round of applause for Shimon, please.